Hey everybody, in this section we're going to be talking about areas of surfaces of revolution. Okay, so areas of surfaces, it's exactly what you think about an area. But a surface, the interesting part about what we're talking about in this section is how the surface is formed. So if you think about what a surface is just the outside or outside layer of a volume, or an outside layer that encloses a volume. So like my pen, for example, the surface is every part of it that I can touch. So the outside layer that encloses an inner volume. So right now we're not interested so much in the volume, like what's inside of that surface, just what's the outside and what is the area of that outside. Now a surface can be formed, so the surfaces we're talking about is surfaces that can be formed by revolving a curve around an axis. Okay, so we don't just have like a random surface that we're talking about here. We're talking about surfaces that come from when you take a curve and that curve rotates around an axis, and that's the surface that gets formed. So let me try to draw you a quick picture of what we're talking about. I'm going to try to draw a 3D picture, but I'm limited to 2 dimensions here. So imagine this is your x-axis, and you have some kind of curve. I'm going to use the curve y equals square root of x. So it looks kind of like this, roughly. Okay, let's say I stopped right here. So that's a curve, and I'll say it's y equals square root x. And I'm going to take that curve, I'm going to start rotating it, and I'm going to rotate it around the x-axis. And so what would happen is I would form this region here, or this surface. So it would rotate around and then go behind the axis and come back up. And then I would get this surface of this region. And so this outside layer is what we're interested in. What is its area? And so the way that we're going to figure this out is we're actually going to take these surfaces and we're going to cut them into strips. Okay, so just imagine along this surface, if I just sort of cut out a strip of it. Okay, so if you can, picture this as 3D, so that's like the front part of it. And then back here I would be going behind. Okay, and then let me get the rest of this. Okay, so I could cut out this strip from my surface, and then what's interesting is if you were to cut that strip open and unroll it, so it's sort of like a piece of paper. Let me just grab a random paper here for you. Right now I have something that's curved, okay? But if I slice it and unroll it, it's actually just a nice rectangular shape. Okay, so what we're dealing with here is this rectangular shape, and then we know things about rectangles. It's going to help us figure out the area of this surface. So I'm just kind of deriving this formula for you that we're about to go through. So if you think about this edge here of this rectangular piece that was the strip that we cut out, initially had it in this circular type shape. It was the edge of a circle. So from previous math, we know that the edge of the circle is the circumference. And so the circumference of a circle is 2 pi times the radius. Okay? So that's going to be like the height or length of this strip that we cut out. And then what we have for this width, so we're going to call that width ds. And it's just this change in the width here, or change in the arc length. Okay? Now, again, this was from a circumference of a circle, circumference. And then over here is the arc length differential. So arc length differential. And we did just talk about arc length in the 6.3 video. So differential. So what we're going to do, essentially, to figure out the area of this surface is take the sum of all of these areas of these bands or strips that we cut out. And so we take this one, we add it to this one, this strip and this one and so on, and we add up all of those areas, and that gives us the full area of the entire surface. And so I'll formally give you the definition for that right now. So our formal definition for this area of a surface is given right here. So first, this is kind of like our fine print here. If our function is positive and it's continuously differentiable on our interval from a to b, then the following is our area of the surface. So the area of the surface, and this is the surface that we get from generating, or is generated by revolving a graph around an axis. Okay, so the area of the surface generated by revolving the graph y equals f of x about the x-axis is, and this is a capital S, not to be confused with lowercase s from our arc length video. So capital S is our surface area, or area of the surface. It's the integral from a to b. And then notice what we have here. We had broke down our surface into these rectangular bands or strips. So this is just like width times length from what we just talked about. So the width was, or like the height in my drawing, 2 pi r for circumference, but the radius is y because that's the radius of our surface. If you think back on the picture, let me just redraw it really quick, that we had here. The y value is the radius. So from this axis that we're revolving around, this forms the radius. So that's why the radius is the y value. And then ds, our arc length differential, was all of this from what we talked about in 6.3. So this is our area of our surface integral, and we'll use this to go ahead and calculate the area of a surface generated by some kind of revolving of a graph about an axis. So jumping right into our example here, we have find the area of the surface generated by revolving the curve y equals 2 square root x, and this is for x between 1 and 2, specifically about the x-axis. So I'm going to go ahead and erase this picture, even though it's actually pretty similar to what we're going to have for this case, because we also have a square root function, and that's what I happened to draw a minute ago. But let's go ahead and jump right into what we need to use for this integration. We do need a y value, but we know what y equals, and we do need the derivative of our function y. So let's go ahead and start with the derivative. So first, let's go ahead and find the derivative of our function. I'm going to call it dy dx, just because our function was named y. And so our derivative here, if you rewrite this as x to the 1/2 power, this is 1/2 times 2x to the negative 1/2. Okay, I brought down the 1/2 power and I subtracted 1. Let's make this look a little better. The 2's divide out. This is x to the negative 1/2, which can be written even better as 1 over square root x. Alright, so there's our derivative. It's going to go into our integrand and we're going to square it. And then we're going to substitute what y is in terms of our function with x. So I'm going to plug into this formula for our area of our surface. So from 1 to 2 is what we're integrating. 2 pi times y, in our case y is 2 square root x, times the square root of 1 plus our derivative squared. So 1 plus 1 over square root x quantity squared dx. Okay, so we've used our formula. Let me go ahead and get that out of the way. And then the rest of this, the setup is done. It's just simplifying it and getting it into a form where we can integrate it easily. So this is 4 pi on the outside. Integrate from 1 to 2, square root x. And then in here, when we square, this is going to be 1 plus 1 over x. Okay, because I square away that square root down there on the bottom. Okay, so I'm going to go ahead and combine these, and we get x times quantity 1 plus 1 over x. Now I can distribute this x, but actually what's going to help out is if I go ahead and get a common fraction, common denominator here. So let's go ahead and times this 1, right, x over x. Okay, so times that 1 by x over x. And then this looks like square root x times x plus 1 on top over just a single x on bottom because it's the common denominator. And then that actually lets us just divide out those x's. And so we end up with square root x plus 1. That's what we end up with our integrand becoming. All right, so going right along with our integration, I'm just going to use U-substitution real quick here. So this is 4 pi integrating square root u. 1 dx is the same thing as u, so just du. I'm not going to worry about changing my limits of integration this time. Instead, I'll actually just resubstitute what u is before I plug in my limits of integration. So this is going to be 4 pi. This is u to the 1/2 right now. So when I integrate, that becomes u to the 3/2 over 3/2. And then let's make this look better. This is 4 pi times 2/3. And then this is the point where I'm going to go ahead and bring x back in because I never changed my limits of integration. So I'll say x plus 1 to the 3/2 power. So I'm just replacing u right now. And then I'll keep going from there. And now I can plug in my limits from 1 to 2. We have, looks like 8 pi over 3 out front here. And then x plus 1, I'm going to rewrite this as square root to the 3rd power. That's the 3/2 power. Just a quick note on 3/2 power or a rational exponent like this. You can bring this power, this numerator, inside if it's easier. So I can actually put that here if it would have been easier. But a lot of times it's easier if it's outside. But just know be aware, you can put it on the inside of the radical. So this becomes 8 pi over 3 times cubed root of, and I'm going to just go ahead and show all the steps, 2 plus 1 quantity cubed minus 8 pi over 3 times square root of 1 plus 1 quantity cubed. All right, let's see what we get. 8 pi over 3. This is square root 3 cubed, so square root 3 times itself, and then again, so that's going to turn into a 3, and then one more square root 3 is left. And then over here in the back, minus 8 pi over 3. This is square root 2 times itself 3 times, so 2 of those square roots undo, and you get just a 2, and then one more square root of 2. And then final answer, let's see what we can make this look like. Let's go ahead and divide out these 3's, if that's gonna, yeah, just looking at the whole thing. We'll divide that out. So 8 pi square root 3 minus, let's put this together, 16 pi over 3 times square root 2. And there it is. So that number, I know it's not that meaningful in the form that it's in, is the area of that surface between the numbers 1 and 2 for the x values. So let's see if we can, I'll tell you what that is with a decimal so it makes a little bit more intuitive sense. So about 19.8 square units is the area of our surface.